Can I ask the people in the second half to move up? Yeah. We'll give people a bit more time to come in, but in the meantime, it's a great pleasure to introduce our publisher, Marina, who will speak a little bit about this special lecture.
Thank you, Jackie, and thanks everyone for coming this morning, and I hope you have been enjoying so far. But I'd just like to briefly introduce this lecture, which is a Materials and Society lecture, sponsored or supported by our Materials Today brand. And from construction and electronics through energy and medicine, materials science and engineering has made significant and enduring contributions to the lives of every human being. The Materials Today Materials in Society lecture reveals how materials science is tackling real-world issues, exploring the huge improvements, the applications of research, and making the way for us to live and work today. This year's lecture at Nano Today 2017 is in honor of the pioneering scientist and engineer Professor Mildred Dresselhaus, who sadly passed away earlier this year. And now Professor Jackie Ng will introduce this year's lecturer, Professor Linda Nazar. Thank you.
Thank you, Marina. Before I introduce Professor Nazar, I want to just share a quick note about Professor Mildred Dresselhaus, who was really a senior faculty member. She was an institute professor at MIT when I was there in the chemical engineering department. And actually, Millie and I shared two students, one from physics and one from electrical engineering. She's really a wonderful person, and I was so glad that last year, in a conference in Quebec City, I had the pleasure of meeting her after many years. She's really a wonderful person to work with, always generous and giving to her colleagues and her students. I really miss her very much. So today, it's a great pleasure to introduce the next speaker, next plenary lecturer, Professor Linda Nazar, who will be giving this special lecture. Okay, and Linda actually is currently a Senior Canada Research Chair in Solid State Energy, Materials, and Distinguished Research Professor at University of Waterloo. And she's a Fellow of the Royal Society and an Officer of the Order of Canada. And she has won numerous awards and highly recognized for her work. In particular, she delivered the August Wilhelm von Hofmann Lecture to the German Chemical Society, and is on the Web of Science 2014, 2016, and 2017 highly cited researcher list, and also the 2014 most influential minds. Linda, it's a great pleasure to have you here. Look forward to your talk.
Well, thank you, Jackie, and thank you, Elsevier, for making this possible. Thank you for all coming this morning after that wonderful luau. I recognize the dancer over there, I think. So I'd like to start my talk by acknowledging the tremendous work of Mildred Dresselhaus. In principle, this works. It did earlier. Sorry. There we go. It was just stuck. So I met Professor Dresselhaus a few times in her later years. She was truly a remarkable woman with a remarkable career. These are just some of her awards, the ones that would fit on the page, basically. So, for example, you see that she won the IEEE Medal of Honor. She was the first female recipient. She won the Presidential Medal of Freedom. This is her receiving this award at this point. She was also a classical music player, she was a violinist, and she had a chamber orchestra. These are some pictures of her earlier on in her life. And she was also the first woman to win the National Medal of Science. So as I said, one could go on and on, but she was a highly decorated woman and is considered, of course, to be the queen of carbon science, in particular with respect to her initial work in carbon nanotubes and then following her work in graphene. And what I know most about her was what my PhD advisor told me once, which is that she used to bake cookies for her group meetings. And as someone who can barely organize their own group meetings, I was always horribly impressed with this. So she sadly passed away in February of this year, and we all, I think, as I said, are a great debt to the field of carbon. And she had a passion for energy as well. This is a citation of hers that I found on the web, pointing out that energy is one topic on which different countries can work together collaboratively. This is actually hardly happening. And if we can all produce energy from an element that's available in abundance on our planet, that would be a good thing, but we have to learn to produce energy in large quantities cheaply and without detriment to the environment. And I think those are very wise words. So with that, I would like to this is sort of the overview of things. How do we develop sustainable energy for our future? And there are many different components to this. I would say that electrochemical energy storage is certainly key. So as we take energy from sustainable renewable sources, solar for certain, wind, and I mean we must remind ourselves that there's enough solar energy in the planet to power our environment for many decades. So this energy is then stored into batteries, and this can be then delivered to cities to provide energy efficient and resilient infrastructure, which of course allows us also to power the Internet of Things and the grid, and allows us to achieve, in some time in the future anyway, autonomous vehicles. And so actually batteries, or energy storage devices as we like to call them, are a very important part of all of these components, including even in cities. But I'm going to mostly focus just on the batteries themselves, the energy storage, and remind you that innovation for these systems is based on novel material and design and device concepts. And I'll be, of course, focusing a little bit more on the materials today. So those of us in our field consider energy storage to be a challenge of the 21st century. In the past, of course, we all needed rechargeable batteries for our laptops and video cameras and things of the sort. But now, as I just mentioned, we need batteries to store energy from renewable sources to make that energy intermittent. We need to power the world both for big computing and for small devices. And this requires energy delivery on the watt-hour to megawatt-hour level. And of course, we need to enable low-cost and high-range electric vehicles. This just shows a bus in Africa. And this is at the kilowatt level. So the energy storage needs go all the way from the small to the very large. And they all have in common the fact that we are taking chemical energy to electrical energy to provide work. That's the downhill, or delta-free, negative, the free energy being driving the system downhill. Sorry, can't speak. And of course, in the reverse, when we recharge the cell, we're taking that electrical energy back to chemical energy, which is taking that free energy and pushing it up when we plug in our system. So the point here is that these different energy needs all need different materials, because then they also have a different cost point. What is favorable for running your laptop is not necessarily going to be appropriate for running an electric bus. Or, for example, the grid, where really costs have to be less than about $50 a kilowatt hour. And that provides real challenges, not just for the chemistry and the materials, but for practicality. So I'll be talking about, just to give you a brief introduction, because I suspect there aren't that many electrochemists in the audience, so I'll give a brief lecture on lithium ion. And then I'll mostly talk about some solid-state batteries where nanotechnology can play a role, and multivalent intercalation where it's important, and then ending off in some lithium-sulfur batteries. So for those of you who are not familiar how a typical lithium-ion battery works, probably most of you are, but just in case, on discharge, oops, my button got away from me here. Let's start again. So on the discharge, on the charge aspect of the cell, the lithium ions are placed into the layers of typically a graphitic type of carbon, and they are deintercalated from typically a layered metal oxide, and lithium cobalt oxide is the favorite. It's still used in the Dreamliner, although other metals have since replaced cobalt. And on the subsequent discharge of the cell, this process is basically repeated. So we have it's called a double intercalation system. The lithium ions either lie between the layers of the carbon or between the layers of the oxide. And on charge, these cells can get up to fairly high potentials, up around 4 volts versus lithium, whereas at the negative electrode, we're fairly close to the reducing potential of lithium. And what's particularly important in these cells is not just the materials at the negative electrode, as we call it, and the positive electrode, but also the electrolyte that lies is this little fuzzy blue stuff in the center. So that contains a lithium salt, and usually an organic, which typically these days is ethylene carbonate, dimethyl carbonate mixture, but a variety of carbonates can be used. And the interfaces are the real problem because that organic electrolyte is fundamentally reactive. So when we talk about progress in lithium-ion, what do we need to be happy to invest in Tesla motor, for example? We think about where lithium ions have come and where they're going. And this is a source from Sony showing the progress over the years, starting at about 1990 all the way up to about 2014. Sorry about the graph being a little fuzzy. But the point is that there has been an increase in energy density year by year for these things that we call 18650 cells, which are like a really big AA battery. But it is generally acknowledged that that limit is about 280 watt-hours per kilogram. And so that's way over here somewhere, but that's about it. This is an asymptotic curve. And so this is the limit for batteries that operate on that intercalation chemistry that I just showed you on the previous slide. And in any cell, whether it operates by intercalation or it's a lead-acid battery, we have the electrons stored per mass, which is usually sort of coulombs per gram, or we can also count that in coulombs per liter, which would be a volumetric energy density. And this is particularly important, and it's a concern for nanomaterials, because we don't want massive cars with a massive battery. So these batteries, especially for automotive transport, have to be fairly dense. In other words, they have to have a good volumetric energy density. I'm having a little trouble with my control here. Is there something you can do to it stop working all of a sudden? Okay. Sorry? Sure. Because mine seems dead. Where is the house one? No, it's not the batteries. I actually changed them. Let me just try again. No? Full batteries. I think it's maybe Well,
I just put ours on. So.
Okay, where is that? Okay, thanks. Right. I'll use this as my pointer. So as I was explaining, energy density is really vital in energy storage systems because we don't want big fluffy cars. And so this is one of the main concerns for car manufacturers today. Of course, we also want these cells to be lightweight as possible, so it's not as if the gravimetric energy density isn't important, it's just that the volumetric at the moment anyway takes precedence. And if you multiply the capacity by the voltage, you get, as I said, the energy density, which are those values that I quoted in either watt-hours per kilogram or watt-hours per liter. So this is the line that shows sort of where we are right now, 250 watt-hours per kilogram or 800 watt-hours per liter. And these batteries, which were developed basically in Sony in 1990 through the seminal work of John Goodenough and Rashid Yuzami and others, have progressed through the years through a lot of different sorts of cells, including lithium iron phosphate, which I think you'll probably hear about from Karim Zaghib later this morning, and many other systems. And these are used now for a plethora of different uses. One in particular that people often forget about are robots. Nobody wants a plug-in robot. They pretty much have to work on batteries, and they have to be very safe, and again, high volumetric energy density because you don't want a huge battery. So then the question is, where are we going with this? How do we actually get to a 2 times energy density and less than 2 time factor in cost? Because these are really the factors that are going to drive the field forward. How are we actually going to achieve this? So some of those technologies I'll be briefly mentioning today, and again with an eye on how nanotechnology can help us get there. So this is the critical slide. Here I have plotted the potential of lithium down at the bottom, so it's -3 versus the standard hydrogen couple, but I put it at 0 just to reference everything to it. And here is the redox couple about 4 volts above that of lithium for a typical layered metal oxide, which is what is used in our cars and most devices today. So the point is that at the positive end of that electrode, the electrolyte, as I mentioned before, is unstable to oxidation. And the reason these materials work at all is because they have a passivating coating on the surface, which is carefully designed. And at the graphite, or negative, the carbon end, the negative side, there's also electrolyte instability or reduction. So effectively, batteries work not because of thermodynamics, because there's serious problems at both sides, but simply because of kinetics. One sort of stabilizes these systems somewhat by kinetics. So the higher the surface area, the more the surface reactivity. And therefore, nanomaterials themselves are often actually a detriment for energy storage. And so, but it depends on what the voltage window is. So if you can make your cell work within sort of these narrow limits, then nanomaterials are much more favorable. So we always have to keep in mind the issues of cost, scale up, and we heard some talks about that yesterday, and especially, as I said, the density of the systems, because that is one of the drawbacks that nanomaterials have, which is generally what we call a low tap density. So there's a lot of different areas where nanotechnology has contributed. These are where, in my opinion, where it's an advantage. I already mentioned high voltage materials only work, these metal oxides, because effectively there are additives in the electrolyte that passivate the surface and form thin layers of a polymer which prevents further reactivity and also metal dissolution. At the negative electrode, there's been an awful lot of work done on combining silicon nanoparticles with carbon to increase the lithium uptake. And as we heard yesterday, if you were present in the audience, nanocomposites for sodium electrodes are also being considered. But what I'll be talking about mostly is just a bit about tailored design ion conductor interfaces at the negative and some lithium sulfur chemistry, where situations where nanomaterials really alleviate mechanical stress and improve charge transport at the interface, and also solid-state batteries, which require an intimate mixture of solids on the nanoscale. So I'm going to start at the bottom and work my way up. So Toyota started talking about solid-state batteries in 2014, and they now claim that this is their next big thing. This is from July in 2017. And some of you may have heard that Dyson is also going to start building solid-state batteries, and many other companies are claiming to do so. And there's an awful lot of hype associated with this and an awful lot of challenges. So the advantages, if we take our lithium-ion battery, the advantages are that we don't have the safety concerns of liquid electrolytes. We don't necessarily have a voltage limited at 4 volts, because in principle, solid-state batteries can go up to 6 volts, as long as the electrolyte is stable. And that requires, however, a solid-state electrolyte, and it requires one that's chemically stable. So these have improved safety because they're inorganic materials, and especially they are compact. So you can go from a situation in which you have a typical stack of cells for a lithium-ion cell, and now these are simply stacked in planar arrays. And that really, just that design feature itself really improves the volumetric energy density. And they are quite compatible with next-generation technologies such as lithium-sulfur. And what might surprise you is that they have better low-temperature performance, as Toyota has shown, simply because the ions are moving through a solid and they're not limited by the viscosity of liquids at low temperatures. So here's what a solid-state battery more or less looks like. So it'll have an electrolyte, which is shown by these little yellow circles, and the electrolyte, the solid-state electrolyte, is intimately mixed with some positive electrode material. This could be one of the lithium metal oxides I mentioned, lithium cobalt oxide or something else. And at the negative electrode, one uses either a negative uptake material, or one can actually use metallic lithium. And metallic lithium is preferred, but as I said, it has its own set of challenges. So the problem is really one of what we call a triple phase boundary, which is that in a battery, the electrons have to find their way to the active cathode material to do that redox chemistry at the same time as the ions that move from the solid electrolyte enter that material. So at these junctions of the electrolyte active material, we have this triple phase boundary, and the more triple phase boundaries you have and the more intimate that contact is, the better the cell will work. So clearly trying to make solid-state batteries work on 5 micron or 10 micron particles is going to be a real challenge. And So the benefits are that the reactivity of the liquid electrolyte is no longer a concern because we have solids, but achieving simultaneous, as I said, ion electron transport is really a problem, and that's where we hope that nanotechnology will participate. Now, this is actually beginning to be a fairly large field. Everybody's jumping into it. As I said, as usual, there's a lot of overhype. I'll just tell you a little bit about some solid-state sulfides which have been developed. So the first requirement is that you have a good fast ion conductor. Before you even worry about nano-sizing it, you need to have a good material. And that means it has to have a conductivity in excess of 10 to the minus 4 Siemens per centimeter, because that's limited by the size, the thickness of the electrolyte that you can sustain in the cell. So what really broke open this field for Toyota and many other people was the discovery of a material which we now colloquially call LGPS, which is a lithium germanium phosphosulfide. And this has a conductivity of about 1 times 10 to the minus 2 Siemens per centimeter, and that is actually the conductivity of a typical liquid electrolyte cell. And that's pretty amazing that one can do that in a solid. And so it generated a whole family of electrolytes since it was first published in 2011 that have really driven the field forward. And this just is the structure of LGPS, showing that there's a main conduction path along what we call the C-axis, and this is about 4 times 10 to the minus 2. And in the other plane, it's about 10 to the minus 4, thus qualifying it for the fast ion conductor designation. So, as I said, since then, a lot of lithium-ion conductors have been developed basically by Ryojo Kano in Tokyo while working together with Toyota. And this is the line of a typical lithium liquid electrolyte. So you can see that there's now quite a few materials that have been developed that even exceed this. So for those of us in the field, this is really exciting. Now, nobody's actually been able to reproduce this work in anyone's lab, but sometimes it's a kind of a bit of an art. And I also draw your attention to the activation energy for transport, which is 0.27 electron volts. So both are important: high mobility of the ion in the solid and, of course, high conductivity. So in our search of, Toyota's obviously going off in this direction, and in our search for what goes beyond lithium ion and even beyond solid-state lithium ion, we have to consider the fact that lithium it's not a scarce resource, but there are some issues. The price of lithium has risen 40% since January 1st of this year. It's up to $20,000 a ton. And while it's not going to be really a problem, I would say, for many years, 5 to 10, we can start thinking about sometime in the future when it would be. For example, if 10% of the world's 60 million cars become electric vehicles. Losing my pointer again. Normally okay, here we go. So if 10% of the world is pure electric vehicles, that means 75,000 tons of lithium. And that's right now half of today's lithium production. So we can consider other elements such as sodium, and I'll be talking a little bit about magnesium and zinc before returning to sulfur batteries. Sodium only has a 0.3 volt penalty versus lithium, so on that redox scale that I showed you, with lithium being at the bottom at 0, sodium is at 0.3, so that's not much of an energy penalty, but there is a bit of a mass penalty. However, as one of the speakers yesterday pointed out, it enables low-cost aluminum current collectors. So there are certainly motivations for going here, but we don't have, at least up until recently, very good sodium-ion conductors. They're the analogy of that LGPS structure that I just showed you. So here's one that we just developed. It has a conductivity that's just 1 order of magnitude below LGPS, but it certainly qualifies as a fast ion conductor, about 1 times 10 to the minus 3 at room temperature, with an activation energy that's even a little bit less than that of the famous LGPS. And this paper just came out in Energy Environmental Science about a week ago. This shows its structure. It's similar to the LGPS family. It has tin sulfide tetrahedra and phosphorus sulfur tetrahedra, with the channel shown here of sodium ions, and they're shown as little tiny red dots. And the important point is the activation energy and, as I said, the conductivity. But even more important is the fact that our ab initio molecular dynamics simulations show that there is almost virtually isotropic conduction of the sodium in this lattice. So this yellow surface here is the sodium ion probability density isosurface calculated from the AMID simulations. And you can see that there is just a perfect isotropic pathway of the sodium in the structure, whereas in LGPS the conductivity is predominantly one-dimensional. And the diffusion coefficients are also isotropic, which is almost shown, you can see almost that from the picture, but you can actually, we've calculated these in all three directions, and the diffusion coefficient that we've calculated at room, when we extrapolate this value to room temperature, is about 2 times 10 to the minus 8 Siemens squared per centimeter squared per second, which again qualifies it as a fast ion conductor. The predicted value for LGPS is almost the same. This is predicted by Garrett-Cedars group. So we've developed a new conductor that has a new sodium ion conductor that's sort of the equivalent of LGPS. It has isotropic conduction, and we're working very hard right now on making sodium ion batteries out of that material. And the isotropic conduction is important because interface control is all keen, is all important. And obviously having three-dimensional conductivity allows those interfaces at least to be improved in all facets of the crystal. So I'll switch gears now and just talk a little bit about magnesium and zinc divalent cations. We've been working fairly hard on this with the Joint Center of Energy Storage Research in the USA. We're part of their program on this. So the advantage of magnesium versus lithium is that it allows one to use a metal at the negative electrode rather than the graphitic carbon that I discussed for the lithium cell, which means we don't have a double intercalation system. We just have intercalation at the positive electrode, and we have metal deposition at the anode. Now, when I say there's no dendrite formation, which plagues lithium and sodium, it doesn't mean that there really isn't any at all. If you push the system hard enough, you will get some, but it's certainly less prevalent. So if you can use a metal anode, that greatly increases the density compared to the carbon, the fluffy carbon that's used in the ion cell. The disadvantage is that, as you might imagine, a divalent cation is fairly sticky because it's divalent, and so it has strong interactions with the lattice. And there is also a desolvation penalty for those multivalent cations at the interface because they have to strip off their organic solvation shell in order to enter the lattice. So we worked together with a group at Berkeley. This is Garrett-Cedars and Kristen Person to do theoretical calculations. They did the theoretical calculations. We developed the materials. And we're trying to develop an understanding of can we model the activation energy barrier in these systems, and can we actually learn what the critical parameters are. And so this just shows a discharge and charge profile for this system showing very low polarization. We developed what's called a thiospinel, whose structure is shown here, that exhibits twice the capacity of the previous material reported in Nature by Doran Orbach's group, which is a Chevrel phase. And the problem here is that, or not the problem, but the magnesium can occupy both octahedral and tetrahedral sites. And as you go to deep discharge, the magnesium starts to occupy these tetrahedral sites, shown here in red, and it actually gets trapped because the activation energy is a little bit higher for getting it out of there. So that was, that's not necessarily a problem, but it was a bit of an impediment. But what was particularly comforting was that calculations and theory came in perfect accord. So this is a plot of the diffusion barrier, and these data were, as I said, determined from Garrett-Cedars group. So this is a plot of the diffusion barrier, and the value from experiment is 530 MeV, which is our data shown here, whereas theory predicted it to be about 550. These are dilute and concentrated limits here. So that's a pretty good correlation between experiment and theory, this being, as I said, the experimental data, right around 530. But the point is that this is actually a pretty high energy barrier. So you'll recall on the previous slide, the fast ion conductor was sort of 0.2 EV, 0.25 EV. So 0.5 is really high. And that's where, again, nanomaterials then become absolutely critical. So we were fighting this problem of fading capacity in the cell and not understanding why it was fading. And as soon as we nano-sized our titanium sulfide, we now have rather flat cycling over at least 70 cycles. And this is going from the crystalline material to the nano-sized material. Now, we used a very low-tech method to achieve this nano-sizing, which is just ball milling. And so our sizes still range from sort of less than a micron to submicron down to 200. Sorry, that's nanometers, not angstroms. And so finding chemical ways to make these nanomaterials directly, of course, is our next step. So the other problem is that, as I said, this desolvation penalty at the interface is sort of an additional burden that a divalent cation has to pay in addition to limited mobility in the lattice. But if you work with aqueous systems and you have water within the layers, now that desolvation penalty basically disappears. So there's also the divalent cation. It can be screened if you have the solvent, i.e. water, within the lattice. So this is a really promising way forward, but you need an anode that's stable in water, and that's not going to be magnesium, and that's not going to be lithium or sodium. So we turn to zinc, which is also a high abundant metal, non-toxic. It has all the right qualifications, including high volumetric energy density. And so we're developing aqueous zinc cells that are just like an intercalation cell, except we have water as our electrolyte with some zinc salt as the cation, as the charge carrier, and zinc metal as the negative electrode. It's extremely stable. And then we had to develop materials for the positive electrode. And we decided to work on making these nano-sized for the reason that we want to limit the pathway, the transport of that zinc ion in the lattice. So these materials are nanobelts. You can see these are sort of long fibers, and they're about 200 nanometers wide and about 100 to 50 nanometers thick. And the long direction is, fortunately, this is the short direction, the direction of transport in the lattice. So this is particularly the dimension that we had to control, as I said, to about 200 nanometers. And we can actually cast these materials directly as freestanding electrodes. And the material operates by a very interesting process. We actually start off with it pillared with zinc ions, which maintains water in between the layers. And when we put this in the cell, the system swells slightly to add additional water, and then as we fully intercalate the zinc, it squeezes back down again. And so this is completely reversible, and it's almost like an accordion, which is why I show that picture up at the top. So we have zinc insertion where the water is squeezed out, and we have zinc deinsertion where the water fills back into the layers. And that's also why nanomaterials are important, because there's stress associated with that, and without a nanomaterial, the system really doesn't work very well at all. With a nanomaterial, we're able to sustain 1,000 cycles with virtually no capacity fading at all. And we have a very low materials cost of about $40 per kilowatt hour. And this just shows what we call a Rigoni plot of energy versus power. And compared to other zinc systems, a hexacyanoferrate, which is being developed by a company in California, and alpha MnO2, our system shows very good power and energy metrics. So the energy density we've estimated to be about 400 watt-hours per liter, so this is not on par with a lithium-ion system, but stacking these systems is all part of actually making a good pack, a good cell pack, and so it's kind of difficult at the cell level to compare energy densities. This is pretty good to start off with. So then in the last few minutes, I'll talk about some chalcogenide batteries. So chalcogenide batteries cover both oxygen and sulfur, and the reactions are shown here. So these do not operate by intercalation chemistry, as I've been talking about for the last few slides, but rather by what we call conversion chemistry. Namely, lithium reacts with sulfur to form lithium sulfide, or in this case, lithium reacts with oxygen to form lithium peroxide. And this reaction is reversible if, and only if, materials are effectively mixed at the nanoscale. And of course, both of these are very abundant elements. I'm going to focus mostly on sulfur, predominantly because lithium air is still a huge challenge. It offers very, very high gravimetric energy densities, but very limited cycling at present. We have a review article in this, and I think that the sum is that it's a long-term prospect. It may work in the end. We all have to struggle away, but lithium sulfur is more of a possibility these days. There's actually companies trying to develop these cells. And we have a review article on that as well. So comparing the chemistry for the traditional metal oxide cell, which is about 200 watt-hours per kilogram, to what one might be able to get for the sulfur cell, you can see that there's a tremendous advantage in the gravimetric energy density. But the volumetric, again, is the real problem. So these cells are particularly suited for things like unmanned aerial aircraft, where one wants the cell to be lightweight. It's possibly not suited for automobile transport, but we're working on that too. So the problem with lithium sulfur cells that people have been struggling with, and there's been 3,200 papers published since 2009, 3,200, is that this simple reaction between lithium and sulfur to give Li2S has an intermediate, which are a series of polysulfides. And my friend Natasha Balsera at Berkeley calls this a cheese to milk to cheese transformation, because these polysulfides in between these two end members are highly soluble. So while there's a very high theoretical capacity, attaining that in practice is very difficult. So I'll just show you the problems with these polysulfides. So the first step is you oxidize lithium from the negative electrode. The electrons transfer through the circuit. They reduce the lithium. And the first of these series is a lithium polysulfide, S8, and that eventually reduces down to S6 and S4. And all of these little polysulfides are soluble, so they diffuse through the separator, and they react, and they form insoluble lithium sulfide at the negative electrode. This is just shown here on the next slide a little bit better. So now in principle, you can reoxidize them back from this lithium negative electrode, depending on how thick the layer goes. But that process in the cell is basically giving rise to what we call a self-discharge, and that's loss of Coulombic efficiency. And if you're unlucky, you build up a thick enough layer of these insulating sulfides, and the cell simply shuts down. So the key is to have all of that redox chemistry occur in the positive electrode and have none of the sulfides escape to the negative electrode. And that's almost impossible, but we can control it. So carbon, Mildred Dresselhaus's favorite material. So we started off with carbon. We actually started off with carbon in our initial report, which is, was in 2009 in Nature Materials, over here. And then over the years, we and many others were working with very, very beautiful sorts of carbons. These are some spherical bimodal mesoporous carbons that have two pore sizes, one for pushing more sulfur in and the other for allowing these redox reactions to take place. And we and many others published lots of papers. We came up with good metrics for this. But the point is that when you try to do this with high sulfur loadings, it just doesn't work very well. And this is just a pretty picture showing one of these these spherical carbon systems where we use the interior to store the sulfur and the porous shell to do the lithium ion transport. So the problem with the sulfur, as we learned, is that really it doesn't have any interaction with the polysulfides. Carbon and sulfur love one another, but the polysulfides are fairly hydrophilic. And so they simply waft or drift out of the cell. And we did learn this by doing in situ or operando experiments at the APS, where we developed in situ operando cells, and we carried out X-ray absorption spectroscopy, and we determine, we collect spectrum every 15 minutes. We analyze those spectrum, and I won't go into all of those details because it's reported in our paper, but the sum total is those polysulfides are just leaking out of the cell in the presence of carbon. So what we learned is you need a strongly interacting surface. So what we chose was this material, which is Ti407. It's called a Magnesium phase. It's a metallic oxide. And we learned how to make it in nano form, and we call these bifunctional polysulfide sponges because it is metallic, it has high electronic conductivity, so it replaces the carbon because these sulfides are all insulating, and it also binds the polysulfides. And this just shows some electron microscopy images, both in bright and dark field, showing these Ti407 crystals. So the take-home message is that when the sulfur gets reduced to the polysulfides in the surface, as I said, it simply forms disconnected sulfides. They end up in the cell out of electrical contact, and you lose capacity, whereas in the case of the metallic polar system, the reaction occurs basically on the surface, and one ends up with greatly improved capacity retention. So that then set us and a lot of other people on the road to trying to develop functional materials, and there's a whole lot of papers published on this as well. It includes using polymers and sulfides and oxides and a variety of different materials. And I'll just show you one of them, which is, again, it was helped by theory. Our experimental results were helped by theory, where we did DFT calculations looking at a polysulfide molecule adhering to the surface of either carbon, nitrogen-doped carbon, or a graphitic carbonitride, which has effectively 3 carbons per unit. And we're having real technical troubles here. So the tape is down. Letting go just a second. Okay, it's back on. So in the case of the carbon, there is no specific bond. I think we need more duct tape. Can I take that off? Okay, now I have only 2 hands and 3 things. That's okay, I'll make it work. Okay, so we have no specific bonding. And so if you take a look at the results of these calculations with just carbon, with one nitrogen, with two nitrogens, and all the way to the carbonitride, you see that there is much greater interaction once you get up to the graphitic carbonitride. So then it was a matter of figuring out how to combine that, because it's an insulator, combine that with graphene, which we did by literally exfoliating both and packing them back together again. And we're able to achieve almost 15 milligrams per square centimeter sulfur loading. And for those of you who aren't sulfur chemists, that's probably kind of not a good, you don't know what that number means, but it's basically the highest ratio I think that we've achieved at a fairly low electrolyte ratio, again, in an attempt to make dense cells. And we're also looking at methods to completely decrease the solubility of the polysulfides in the electrolyte. So going from a system where we have flooded cells with high solubility to chelate systems where the chelate binds up the electrolyte, whether that be tetraethylene glycol dimethylethoxine or some of these acetonitrile systems. What we do basically is we're trying to work on cells in which now, rather than having the polysulfides in solution, we're carrying out effectively a solid state or a quasi-solid state reaction with very limited solubility. And this is actually how the lead acid battery works, very low limited solubility of the, it's okay, I'll manage my hands, very low solubility of the lead in solution. So, and you can read about that in some of these publications. So then in summary on sulfur, there's chemical confinement, which I already just described. One can envision a system in which you let all of the polysulfides into the cell with a suitable protected lithium negative electrode, and some companies are working on cell designs like this. There's also the limited solubility idea, and then of course there's also the concept of all solid state lithium sulfur batteries. And Samsung are exploring this. It's a very, very difficult area, and I won't be talking about that too much more. So if we want to make sulfur cells function, we have to solve the challenge of the lithium metal electrode. And that means passivating or somehow forming a lithium ion conducting film at that negative electrode. So I explained that magnesium does not form dendrites. Well, lithium metal does, and it does so under circumstances where there is inhomogeneous current density at that interface. So our approach to this was to make some mixed alloy halide nanocomposite films from a very simple reaction, which is shown here. Simply, it's an in situ reaction. We take lithium foil, we treat it with some metal chloride, and that metal can be a zinc chloride, indium chloride, bismuth chloride, something of that sort. And that instantly reduces the metal to the atomic state, which then alloys to form these alloys. So a typical reaction would be the reaction of lithium with zinc to form lithium zinc. And we were motivated to do this by the work of Robert Huggins almost 20 years prior, who pointed out that these materials have very high diffusion coefficients for lithium. So you can see that the diffusion coefficient for lithium bismuth, for example, is on par with that of the famous LGPS, which I started talking about at the beginning of the talk. So these are all about 10 to the minus 6, 10 to the minus 8. As I said, great lithium ion conductors, but they're metal. And you can't drive lithium diffusion across a metal because the lithium will simply reduce on the surface. So this is where the halide comes in, because we actually form, as I said, a nanocomposite mixed at about the 200 nanometer scale at that interface. So the orange is the alloy, and the pale blue that you can sort of see in the interstitial areas here is the halide. And that gives it a resistivity of about 10 to the 4th ohm centimeters, which is enough to drive the lithium underneath the film and deposit under the film. So now there's no lithium on top of the film available for dendrite growth. So it established the resistivity that's denoted or conveyed by the halide in the film is enough to create the electric field, and the alloy itself provides the conduit for the lithium diffusion through the alloy itself. We just published this earlier in the year. We actually have another paper just coming out in Joule on a similar idea on in situ coatings, but I won't have time to describe that. So this just shows the cross-section of the alloy. This happens to be for indium, where you can see the population of indium in this film. It's about 5 microns, and it's not quite nano, but these components are mixed on the nano level, and here you can see the chlorine in blue if it's visible. This is showing the top of the cross-section of the film and then the top layer. So the proof is in the pudding, or in the pictures in this case. We've used operando microscopy to take a look at the cell over 220 cycles. This is in the case of just lithium, and this is the alloy film. And you can see that after about 131 cycles, we start to see pulverization, which is classic for lithium films, and finally complete decrepitation of the surface in dendrite formation, whereas in the case of the alloy halide composite film, there's absolutely no change in the surface. And this allows us to stabilize cycling, in this case over 1,500 cycles, with a variety of these different alloy films with little increase in polarization over the duration of the cycling. But this is kind of for any electrochemists in the audience. So the whole theme here has been, of course, nanomaterials, but also using them in the right way at the right time. And this is just a slide that points out that there's an average of 2 decades from discovery to commercialization. So that was true for Teflon and Velcro and diamond films and lithium-ion batteries, which of course are now abundant in our environment, ubiquitous, I would say. And so hopefully in the future, we might be looking at solid-state batteries being commercialized, maybe even in an earlier time frame than what Toyota predicts, which is 10 years or 5 years. And so with that, I would like to thank Jackie Ging for the very kind invitation to give this Materials Today lecture. I'm really honored, deeply honored to be presenting in memoriam of Mildred Dresselhaus. I'd also like to thank Elsevier for their funding. I'd like to thank my research team and all of our funding agencies. This is our Institute for Nanotechnology. And finally, we owe gratitude to Mildred Dresselhaus, and thank you for your attention.
Thank you, Linda, for a very nice overview of the field and also the latest advances in battery applications. Questions from the audience? Yes.
Hi, Linda. Thanks. Can you hear? Okay.
Yes.
Thanks for this wonderful overview of what's happening in the world of batteries right now. I actually wanted to ask a question about the solid-state batteries, which is exactly the thing you didn't want to talk about. So one of the emerging fields right now is these architected materials, and so they offer a pretty robust platform, at least mechanically speaking, for the solid-state electrodes. Do you have any insights
Are you talking
into that?
about 3D printed batteries?
They don't have to be 3D printed, just 3D batteries, 3D battery electrodes.
Yeah. Yes, I do have some comments about that. I guess the overall comment is that, so the reason I didn't talk too deeply about solid-state batteries is that we're still working on step 1, developing really good electrolytes. But we're in parallel trying to develop the solid-state systems themselves by trying to backfill porous cathode materials or semi-porous cathode materials with our electrolytes. If one can achieve this with 3D printing technique, and I think a good paper on this is about to come out in the literature that I've seen, I think that that's a really very powerful way forward. The question is really how effective it's going to be at producing these things in the mass scales that we need. So I think that might be ultimately the drawback that I can see.
Other questions from the audience? No? No, if not, let's thank Professor Linda Nazar.